In this video, let us get an expression for the velocity of transverse waves in a stretched string. What is a string? A string is any metal wire whose length is much greater than its thickness. When a stretched string is given a vibration, transverse wave will be set up in it. To get the velocity of the transverse waves produced in a string, let us consider this setup. Let us take a long and uniform wire whose one end is fixed and other end is held under a suitable tension T equal to m times g, where m is the mass of the string and g is the acceleration due to gravity. When the stretched string is plucked, transverse vibration will be set up in the string. Let us, for our treatment, let us consider a portion of the string xy which is under a suitable tension, that is the tension at both the ends, held by a tension of T at both the ends. When the string is given a vibration, it produces a maximum displacement, and this maximum displacement in the string produces a hump. Let us take V to be the velocity of the transverse wave produced in the string. Okay, look at the diagram. We are choosing a portion of a wire XY which are held by a suitable tension T at both the ends. In this portion XY, let us consider a very small element P, and let us consider a very small element PQ. And this PQ looks like an arc and it makes an angle 2 theta, and the radius of the arc is small r. We know the tension at the points P and Q are T, and the direction of this tension T are tangential to the element P and Q. So, in the diagram, you could see a tangent has been drawn at point P and Q. These two tangents meet at a point R. We can resolve the tension at P. That is, the T can be resolved into two rectangular components, T sin theta and T cos theta. The T sin theta is the a component which is acting perpendicular to the string, and T cos theta acts parallel to the string. Similarly, at the point Q, we'll have two components, T cos theta and T sin theta. That is, the T sin theta will be acting perpendicular to the string and T cos theta will be acting parallel to the string. So, from the diagram you could see T cos theta and T cos theta, that is the two parallel components due to the points P and Q, are acting in two different directions, and T sin theta, one due to the tangential component perpendicular to the string due to the point P and Q, are acting along the same direction. Hence, the parallel components T cos theta are equal and they are opposite. It is evident from the diagram itself, so they will cancel with each other. But the perpendicular component T sin theta is acting along the direction RO. So, the total tension will acting along RO, which is given by F, is equal to 2T sin theta. So, one T sin theta due to P and other due to the tangential tension acting at Q. So, we have F is equal to 2T sine theta. So the sine theta can be approximated to theta if theta is very small. So f is equal to 2t theta. Let us take it as equation 1. Then let us find what is the mass of the string. The mass of the string is capital M, which is equal to small m into pq. Small m is nothing but it is the mass per unit length of the string, and pq is the length of the string. So to know the mass of the string, we need to know what is the length of the string pq. For this, let us consider this arc. So PQ, it makes an angle 2 theta with each other, and R is the radius of the arc. We have the formula to find what is the length of the arc, which is given by radius of the arc into angle subtended by the arc. So the length of the arc is PQ and radius of the arc is R, and angle subtended by the arc is 2 theta. So capital M, that is the mass of the string, can be given by M into 2 theta into R. For an equilibrium position, the resultant tension provides the necessary centripetal force. So we know the expression for the centripetal force, F is equal to mv square by R. And in place of the capital M, that is the mass of the string, we can write m into 2 theta into R into capital V square by R. So this R and R will get cancelled. We get F is equal to m times 2 theta into V square. So we have two forces from equation 1 and 2. So we can compare equation 1 and 2. So it has 2t theta equal to m into 2 theta into V square. So this 2 theta and 2 theta in the left hand side and right hand side get cancelled. We get V square is equal to t by m, or V is equal to square root of t by m. But we have a relation which connects the velocity and the frequency. So V is equal to n times lambda, where n is the frequency of the transverse wave. So in place of V, we can write n lambda is equal to root of t by m, or n is equal to 1 by lambda into root t by m. The previous equation, that is equation number 3, represents the velocity of transverse waves produced in a stretched string, and equation 4 gives the frequency of the transverse wave. If we take a string of length small l, which is fixed at both the ends, and we pluck it at the center, we could see a transverse wave of single loop is produced. As we could see this in the diagram, then the length of the loop L can be equal to lambda by 2, that is the half the length of a wave. So lambda will be equal to 2 times L. Substituting this in the frequency equation, we get n is equal to 1 by 2L into root t by m. This is the frequency of the transverse wave produced in a stretched string.